Okay, so carbon. This is a class about organic chemistry, and organic compounds contain carbon. Carbon is in many ways a very unusual atom. Let's look at the Lewis structure for carbon. How many valence electrons does carbon have? It's got 4. So carbon, being a non-metal, tends to form 4 covalent bonds. Carbon really doesn't form an ion because in order for it to become a negative ion, it would have to gain 4 electrons. That's a lot. And for it to become a cation, a positive ion, it would have to lose 4. It's kind of stuck right in the middle between filling up its half-filled shell or ditching all the electrons and going down to the next level. So it tends not to do either. It just shares. So it's got these 4 valence electrons. It's going to tend to form 4 bonds. So let's look at CH3Cl, which is chloromethane. So we'll put carbon in the middle. If it forms 4 bonds, well, let's do it with dots first. So there's carbon, there's 3 hydrogens, so I'll draw one of them here, and one of them up there, and one of them down here. And there's a chlorine. And then we need to put electrons on those guys. Each hydrogen has 1 valence electron. It only has 1 electron. The chlorine has 7. So the hydrogen and the carbon will share an electron. We usually represent those bonds as lines, but you can think of them as these 2 electrons just connecting the dots to help you remember that each line is really 2 electrons. And here's another bond, and another bond, and another bond. And by doing that, the chlorine now has 8 electrons. The carbon has 8 electrons, and each of the hydrogens has 2. Remember, hydrogen's an exception. It only needs 2. So normally we would draw the structure like this and leave out all the dots. Any questions? One of the cool things about carbon is that not only does it make 4 covalent bonds, but it can bond with other carbon atoms and form long chains and rings and all kinds of stuff. And because of this, there are millions of organic compounds that are possible. So let's look at propane, C3H8. So the carbons, yeah, I love it when I try to write with the pointer. It just doesn't work. Carbon. The carbons will be bonded to each other, and then they each tend to form 4 bonds. So we could just put those bonds in there. And then hydrogen, because it only has 1 electron to share, can only form 1 bond. So hydrogen is going to be around the outside. So that's the structure of propane. And we look at the carbon and we see that it's got 4 bonds, each bond having 2 electrons. It's got its octet, it's 8 valence electrons. Now we talked briefly about bond energies and about breaking bonds. Well, what happens if we break one of these carbon-carbon bonds? Then we end up with some fragments. So here's, let's put, you have to put energy in. When you make a bond, energy comes out, and to break it, you have to put energy in. So I think of, like if you've got two balls that are glued together, you're going to have to give up energy to pull them apart, right? Maybe not glued together, magnetically stuck together. So they kind of went together by themselves. So here's the rest of that. And this guy right here, this bond, is 2 electrons being shared. So when we break that bond, what do we have? We have this carbon with a single electron on it. I'm going to just draw a squiggly line in here because these guys are separated now. So this fragment here is called a radical. Radicals are molecular fragments that have odd numbers of electrons. So this carbon really only has 7 valence electrons in this structure, and this carbon only has 7 in this structure. Are these going to be stable? No. Radicals are not stable. They're going to react with other things to complete their octets. But that's what a radical is. Polar covalent bonds. Just to review, electronegativity is the tendency of an atom to attract a bonding pair of electrons. And so we talk about the polarity of a bond. That depends on the difference in the electronegativity values for the atoms involved in that bond. If the electronegativities are the same or very similar, the bond is nonpolar because the electrons are shared equally. But if the electronegativity difference is great, then the bond is polar. Here's a table of some of the elements and their electronegativities. We see that fluorine is the highest. And so the trend to remember is that electronegativity increases as you go across a period, and it increases as you go up a group. The way I remember it is fluorine is the most electronegative, and so if I'm comparing beryllium and carbon, whichever one's closer to fluorine is more electronegative. If I'm comparing nitrogen and phosphorus, going up, I'm going towards fluorine, and nitrogen is going to be more electronegative. We're going to see a note about this in a minute. Here's carbon is 2.5, hydrogen is 2.2. That's a difference of 0.3, which is not considered significant. I'll just point that out. So here's what happens. Here we have 2 fluorine atoms. Fluorine and fluorine obviously have exactly the same electronegativity. Their electrons are going to be shared equally. But if we have hydrogen and fluorine, going back here, here's fluorine with 4.0 and hydrogen with 2.2. That's a big difference. The fluorine, being more electronegative, attracts the electrons to itself, and the molecule gets lopsided. There's more electrons over here. It's not an ion. It didn't take the electron, but it's shared unequally. And so this end of the molecule has a partial negative charge. This is a Greek lowercase delta. It's a partial negative. That side has a partial positive. This is a polar covalent bond. The ends are different, just like the North Pole and the South Pole on our planet. The ends are different. The magnetic fields point to the North Pole. Here, the ends are the same. When we talk about polar molecules, it gets a little more complicated. When we just have 2 atoms, it's easy. If the bond is polar, the molecule is polar. But when we have more, then we have to consider how the shapes, the arrangement of the shapes. So water is a polar molecule, and propaldehyde is a, no, that's propanone, sorry, it's propanone, is a polar molecule because of their geometries. And so we'll look at geometries in a little bit here. But we say the molecule possesses a dipole, or a dipole moment. Carbon monoxide is a good illustration. This carbon-oxygen bond is polar. The oxygen's more electronegative than the carbon. And so another way to indicate that is with an arrow pointing to the more electronegative one and a positive at this end. But this carbon-oxygen bond is going in the opposite direction. And so we can think of this as like tug-of-war. the oxygen's pulling this way and this oxygen's pulling that way, and overall there's no movement because they oppose each other. It's really adding vectors in 3 dimensions, but I don't usually run into students that want to talk about vectors, so we won't talk about vectors. But you can have a nonpolar molecule that has polar bonds. And polarity is going to be a big deal in organic chemistry. We'll just kind of skip that one. And this is where I was combining slides and things get kind of messed up. But this is important, this guy right here. Carbon-hydrogen bonds are considered nonpolar because their electronegativities are similar. We'll see a lot of carbon-hydrogen bonds. So the rule of thumb I give my general chemistry students is, if the elements are different, it's probably polar. If the elements are the same, it's always nonpolar. But this is an exception to my little rule of thumb. Carbon-hydrogen bonds are considered nonpolar. Okay? We can also have multiple bonds. I've taught a lot of general chemistry, and so I could just go on and on and on about this, but we need to get through this stuff, so let's try to speed it up. So let's look at carbon dioxide real quick. So valence electrons. Actually, I didn't want to do that. I'm going to leave this guy out. Carbon has 4, oxygen has 6, and they're going to share in a way that gives them 8. So if we share this guy and we share this guy, these pair, we're closer, but we still don't have 8 valence electrons for everybody, right? And so what happens is carbon and oxygen are going to share another pair of electrons, and these two are going to share another pair of electrons. And we end up with what's known as a double bond. So this is carbon in the middle, and a double bond to the oxygen, and a double bond to the other oxygen. And if you want to show lone pairs, it would be out here. See, carbon is going to have 4 bonds. These are 2 single bonds, but they're between the same elements, same atoms, and so they're a double bond. 2 pairs of electrons being shared. A triple bond is the same thing, but with 3. So hydrogen cyanide is going to have a triple bond between the carbon and the nitrogen. But again, the carbon has 4 bonds. Almost always, the carbon is going to have 4 bonds. Any questions? 3 lines, 3 pairs of electrons. 2 lines, 2 pairs of electrons. 1 line, 1 pair of electrons. Carbon atoms can form single, double, and or triple bonds with each other. And one term that we use is hydrocarbons. A hydrocarbon is a compound containing only carbon and hydrogen. And so there's the name hydro for hydrogen, carbon for carbon. So let's just draw a couple of hydrocarbons that might have double bonds. Good grief. So we could have something really simple like this. So it's important to understand the whole idea of the valence electrons and the octet rule and the number of electrons around it. But for carbon, which is mostly what we're going to be looking at, it really comes down to 4 bonds. Carbon doesn't have lone pairs. It's got 4 valence electrons. It forms 4 bonds. And so if we had something like that with a triple bond, this carbon has its 4 bonds just with other carbon atoms, and this one does also. But this guy on the end only has a single bond. So he's going to need to make 3 other bonds, and the guy on the other end would have 3 other bonds. And in a hydrocarbon, those bonds would be with hydrogen. So hydrogen is kind of the fall fallback friend, you know. Well, if I can't find anybody more interesting to go to the movie with, I'll take hydrogen, right? Oh, we need some more people to get this discount or something. Oh, hydrogens will come, they'll come, right? They don't have anything better to do. Valence is a real important idea, especially when we start drawing structures of organic compounds, because they generally follow the valence of an element. The valence is the number of bonds that an element can form. And it usually equals the number of electrons that are needed to fill the valence shell. So we've already talked about carbon. Here's carbon with its 4 valence electrons. Carbon has a valence of 4 because it needs 4 bonds to get 8 electrons. Let's look at nitrogen. How many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. How many bonds does nitrogen need to make to get 8? 3. So nitrogen has a valence of 3. Nitrogen usually forms 3 bonds. What about oxygen? How many valence electrons? 6. 1, 2, 3, 4, 5, 6. How many bonds does it need to make? 2. The number of bonds it needs to make, which is the valence, corresponds to the number of unpaired electrons in the Lewis structure. If we look at something like chlorine, what's the valence of chlorine? 1. And so these follow group numbers as well. So the noble gases don't make compounds, so we ignore those. And over the halogens in group 7A all have a valence of 1. We go over 1 more. Oxygen and sulfur and selenium, valence of 2. Nitrogen and phosphorus, valence of 3. Carbon, silicon, valence of 4. Okay? And knowing this really helps with drawing correct Lewis structures and just correct structures in general, because most of the time they'll follow their valence. So use valences to draw the structures for fluoromethane and CH5N. Don't want to go to the name of that. Okay, so what's the valence for carbon? 4. And for hydrogen? 1. Hydrogen is trying to be like helium, so it needs 1 more bond. And the valence for fluorine? 1. So fluorine and hydrogen can only make 1 bond each, and the carbon needs 4. The carbon, therefore, has to be in the center. And we'll have the hydrogens and the fluorine around it. And which position you put the fluorine in doesn't matter. It could be the top or the left, doesn't matter. CH5N. Well, we already decided that carbon was 4, hydrogen is 1. What's the valence of nitrogen? 3. That's its number of bonds, right? So we've got a carbon in here. Those hydrogens are going to have to go on the outside because they can only make 1 bond. So the carbon and the nitrogen must be bonded to each other. And then we've got 5 hydrogens that we can stick around. Well, let's see, if we go 1, 2, 3, 4, 5, that would satisfy the valences, wouldn't it? So this carbon would have 3 hydrogens bonded to it, and the nitrogen would have 2 hydrogens. But the nitrogen now has 1, 2, 3 bonds. That's what it wants to have. The carbon has 4 bonds. What's not shown here is that there's a lone pair on the nitrogen. That's where the valence, the rest of the 8 electrons is. Any questions?
Why wouldn't it be a double bond?
Why wouldn't it be a double bond? That's a good question. Well, let's try that. Let's get rid of one of these. What do you want to make the double bond with?
Carbon, nitrogen.
The carbon. Okay, so, yeah, I can't write with the eraser. Put a double bond there. So now carbon has 5 bonds, right? So that means we have to get rid of one of these. And so nitrogen has 1, 2, 3 bonds, and carbon has 4 bonds. So those guys are happy with their valences, but this doesn't work with this formula of H5. You could have a compound like this, but this is going to have a different formula. That's going to be CH3N. Different compound. Yes?
So when you say you want us, like, the valences,
Mhm.
that's equivalent to the bond numbers.
The valence is the number of bonds that that atom tends to form. There are exceptions, but usually you'll see nitrogen forming 3 bonds, oxygen forming 2 bonds, carbon forming 4 bonds. In many ways, organic chemistry is a lot more predictable than general chemistry. So that's something to look forward to, predictability. So a review of writing Lewis dot structures. You need to know the total number of valence electrons. Then you make a skeletal arrangement. And now that we've looked at valence, valence helps us to make that skeleton. Next, you're going to take electrons and spread them around to give each atom an octet, except hydrogen. If you don't have enough, then you're going to have to make double or triple bonds. And then we're going to learn how to compute formal charges and evaluate the structure. So let's just do some examples. Here's phosgene, COCl2. Well, first thing is, how many valence electrons? Carbon has how many? 4. There's an oxygen that has 6, and 2 chlorines, each 7. So there's 14, and 6 is 10, 20, and 4, we got 24 electrons to mess around with. Now, writing this skeleton structure, there's carbon. Carbon wants to make 4 bonds. So we've got carbon and oxygen and chlorine. How many bonds does chlorine want to make? 1. So let's put a chlorine in here and a chlorine in there, and that'll satisfy the valence for chlorine, 1 bond each. Now carbon has 2 more bonds that it wants to make. We have 1 more atom, oxygen. Oxygen wants how many bonds? 2. So can we accommodate that? Sure we can. We're just going to not make this a single bond. We're going to make this a double bond to the oxygen. Because in this way, carbon has its valence, oxygen has its valence. We're good here. Now we've got electrons to deal with. Each of these is 2 electrons. 2, 4, 6, 8. 10, 12, 14, 16, 18, 20, 22, 24. Carbon doesn't get any because it already has 8 from its 4 bonds. So when you follow the valence for these atoms, it'll usually take care of itself, and you'll have enough electrons to throw around as lone pairs. There's a whole bunch of examples in here. Let's just do this one just because it looks kind of crazy. This is glycine, which is an amino acid. As we will learn, we often write formulas for compounds in a way that's a little different than general chemistry. In general chemistry, we would have combined all of those hydrogens together, and we would have put the carbons together. But this is giving us a clue as to how these things are connected. So NH2 suggests that the hydrogens are attached to the nitrogen. I'm actually going to skip the number of electrons first and go straight to the skeletal structure and come back. So this is suggesting that there are 2 hydrogens attached to the nitrogen. And next is a carbon, H2. Those 2 are on the carbon. And the next is carbon with an oxygen attached to it, 2 oxygens. And this H being at the end here, it's probably attached to the oxygen. So we're just looking at valences right now. Does nitrogen have a good valence? Number of bonds, it wants 3. How about this carbon? Yep, that one's good. How about this carbon? It wants another bond. Does anybody bonded to it want another bond? The oxygen on the top, he wants 2 bonds. This oxygen's fine, because he's got 2 bonds. Okay? Now we can go and figure out the number of valence electrons. We've got 5 plus 2 plus 4 plus 2 plus 4 plus 12 plus 1. That's way too much math to do in my head. Let's see. 12, and those guys, that's 20, 24, 30? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Understanding valences makes drawing Lewis structures a lot simpler. I'm not sure why we don't teach it in general chem, but we don't. Okay, so we did not get nearly as far as I wanted to, but we'll figure it out. So come on Thursday, and we will be doing some more lecture and be working on a worksheet just to review these concepts. Okay? And hopefully Blackboard will be functioning for me by then.